Arkadaşlar, in the class we have started discussing about the very important properties of systems, and we mainly discussed two different properties. One of them was linearity. Linearity. It was about like a times x1 of t plus b times x2 of t. If this combination, linear combination of two signals like multiplied with certain scalars is entered to a system, okay, this is my system, and the output will be a times y1, which is the output of the first input, plus b times y2 of t, which is the output for the second one. If I add two inputs together, I will also add two outputs together. Okay, that's the linearity property. As I said in the class, linearity property includes a times x1, a times v1, which is called scalability, and this addition is called superposition. Okay, so these two things should remind you of linearity, and our systems in this class will be dealing with linearity problems. The second property is like time invariance. Okay, time invariance. What does time invariance mean? If I enter or if I feed one input to a system, I will obtain y output as y of t as my output. Okay, this is my input signal. This is my output signal. If I shift my input signal t0 seconds, okay, to my system, I will obtain as my output again t minus t0. If I shift input t0 seconds, I should shift the output again t0 seconds. Okay, that's called time invariance. So when I call TLTI systems, in which we will tell you this is our system like, okay, linear time invariant systems. So if we talk about linear time invariant systems, like this box, okay, our RLC circuit, our op-amp circuit, anything like that would work like a LTI system, okay, the input and output ports. So what is important about LTI systems is that I will mainly remind you of this property. Okay, if I can say that any signal, okay, any signal can be represented, can be represented as the linear combination of basic building blocks. Okay, combination of basic building blocks, okay, in which we will building blocks means we will use Dirac-T and Dirac-N in our applications. Okay, so any signal will be represented as Dirac-T and Dirac-N. What I would like to remind you of is that now if I have an input signal to my system, arkadaşlar, okay, this is the impulse function, okay, impulse function or impulse signal, unit impulse function. I should get impulse response. Okay, this h of t is my impulse response. Why this h of t is important is that h of t characterizes our system. Okay, like how does it behave? What kind of a system is this? Is this a a linear system? Is this a causal system? Is this a stable system? We will talk all about these properties of systems, and we will mainly analyze h of t. It is called impulse response. My input is impulse, darbe fonksiyonu, impulse function. My output will be darbe tepkisi, impulse response. Okay, so if my impulse function is a discrete system, if I have a discrete system, this is a continuous time system, okay? And if I have a discrete time system or discrete system, if my input is Dirac n, the output will be h of n. So h of n, again, it's an impulse response of a discrete time system, which characterizes my discrete time system. Okay, so these are critical properties. These are critical, let's say, definitions of impulse function and impulse response. We will also say, for example, if I have u of t as my input to my system, continuous time system, I will obtain s of t, which is step response. Okay, step response. Why is this step response? Because this is unit step function, okay? Unit step function. Then it is like step response. Unit impulse function is the input, impulse response is the output. Unit step function is the input, unit or step response is the output, okay? Similarly, if I have u of n as my input, and then this will be my discrete time system right now, I will have S of n, which is like, again, step response of my discrete time system. So now let's move on to another step right now, arkadaşlar. If I have, using the linearity property and time invariance property, if I have Dirac n as my input to my system, okay, I will obtain h of n as my output. If I have a times Dirac n as my input, then what should I get as my output? A times h of n. Because if I have an input like this, I will have an output like that, x, y, okay? If I multiply input by a, I should multiply input by y, okay? This was like scalability, right? Scalability. If I have Dirac n minus 2 samples, then I should have h n minus 2. Okay, this is time invariance, if you remember these two topics. Now, what I should say to you, using the linearity property, if I add a times Dirac n plus Dirac n minus 2, if this is my input to my system, then I should obtain a times h of n plus h of n minus 2. Okay, so this is a kind of a very important property. If I add, again from superposition, if I add two inputs, I should also add two outputs together. Okay, so if I give you any input now using Dirac n's, you can easily find out the outputs using h of n's. Okay, if h of n is given to me, for example, in some problems, I will give you, this is h of n, this is my impulse response, and now do the exercises or find the solution, then you should use h of n as such, okay? Similarly, if I have a times Dirac of t plus Dirac t minus 2, okay, then I should have as my output a times h of t plus h of t minus 2. So similar in discrete time and continuous time, using linear linearity and time invariance systems. Okay, so this is the first part, and I would like you to understand this part clearly right now.